All right, this is the notes video for slides 33 through 37. All right, so in section 1.6, we're talking about continuity, right? So these examples say find each point of discontinuity and identify the type. All right, so first of all, we want to think about when could a discontinuity occur, right? Remember, a discontinuity occurs first and foremost anytime the function is undefined, right? So that's a first thing to do. So we look at these rational functions and we realize that anytime the denominator is equal to 0 is going to be when this function is undefined. So we're going to set the denominator equal to 0. All right, so x squared minus 4x plus 3 equals 0. All right, so I'm going to factor x minus 3 and x minus 1, right? And so x equals 3 or 1, right? So remember, what does that mean? That means that x equals 3 or 1 makes f undefined, right? All right, so if that makes f undefined, then we know that there is a discontinuity there, right? So now we just need to think about what type. Well, you know that if you have f of x equals x plus 1 divided by x minus 3 and x minus 1, right? You know that nothing is going to reduce, right? So since nothing reduces, we know that when we evaluate the limit as x approaches 3 or the limit as x approaches 1, we are going to get that these limits do not exist, right? So let me say this. The limit of f of x and f of x, right? And so how would we know that they do not exist? Well, because when I plug 3 in, right, I'm going to get 3 plus 1 is 4 divided by 0, right, which is going to lead us to the fact that this limit does not exist and that there's a vertical asymptote there, right? In this case, 1, so we get to 2 over 0, and this is going to lead us to the fact that this one does not exist, right? And so we could say f is not continuous at x equals 3 and 1, uh, and they are infinite discontinuities. All right, so now what about number 2? All right, so same thing. I'm going to set x squared plus 3x plus 2 equal to 0. And when I do this, I can factor and get x plus 2, x plus 1, right? And so that means x equals negative 2 and x equals negative 1 are going to be discontinuities, right? And so we can say x equals negative 2 and 1 makes f undefined, right? So just like the last one. But now when I see that f of x is x plus 2 over x plus 2, x plus 1, I recognize that I can reduce, right? And so if I reduce, I'm left with just 1 over x plus 1. Now, remember, negative 2 still makes the original function undefined, but now we know that when I evaluate the limit as x approaches negative 2 of f of x, right, I would factor reduce, and then I would plug into the new version, and I get 1 over negative 2 plus 1, 1 over negative 1. And so I get that this limit equals negative 1. So since the limit exists, that's going to mean that there is a removable discontinuity at negative 2. But at negative 1, we know that when we take even the reduced version, we're going to get 1 over 0. And so that is going to lead us to a limit that does not exist. Okay, and so we would say there is a removable discontinuity, sorry, at x equals negative 2 and an infinite discontinuity at x equals negative 1. All right. All right, moving on to slide 34. All right, so now, okay, same directions, but now we have these piecewise functions. So what we have to remember is that each of these pieces individually are all going to be continuous, right? So all of these, right, it's a parabola, a horizontal line, a line with a slope of 1, parabola, line with a slope of -1, right? So they're all continuous by themselves, right? There's no jumps, holes, asymptotes, anything like that. But what we do want to worry about is what is happening at x equals 3. All right, and over here, what's happening at x equals -2. So now we want to remember that when evaluating continuity, we need to evaluate, first of all, does f of 3 exist, right? So f of 3 is 2, so that's nice. Then we want to evaluate the limit as x approaches 3 of f of x, right? Now, in order to evaluate the limit as x approaches 3, we're going to evaluate the limit as x approaches 3 from the left and the limit as x approaches 3 from the right of f of x. All right, so we evaluate limit as x approaches 3 from the left. So that would be by evaluating 3 into the top piece, right? So if I evaluate 3, I get 3 squared, right? 9 minus 5 is 4. And then I get the limit as x approaches 3 from the right. So now we're going to plug 3 into the bottom piece. 3 plus 1 is 4, right? And so what does that mean? Since these are equal, that means the limit as x approaches 3 over all of f of x is equal to 4. But f of 3 is not equal to the limit as x approaches 3 of f of x, right? And so since those are not equal, the function is not continuous at x equals 3, but what kind is it? Well, the limit exists, right? So the limit exists, but the y value is different, right? And so this would be a removable discontinuity. At x equals 3. All right, next one, same idea. So we're going to evaluate at -2, so f of -2. So first of all, -2, we plug into the top piece. So -2 squared plus 3. So 4 plus 3 is 7. So then I want to evaluate the limit as x approaches -2 from the left, and then the limit as x approaches -2 from the right. Obviously, both of f of x. All right. And so if I do that, well, from the left, we're just plugging into the top piece again. So that's going to be 7. From the right, now we're plugging -2 into the bottom piece. So 7 minus -2 is 9, right? And so we can say that these two are not equal to each other, right? And so that tells us that the limit as x approaches -2 of f of x does not exist, right? And so the limit does not exist. So what's the situation here? Well, we have on the left of -2, we are coming into a closed circle, and on the right of -2, we are going out of an open circle, and so this would be a jump discontinuity. So jump discontinuity at x equals -2. All right, moving on to slide number 35. All right, so explain why f is not continuous at x equals 2. Well, remember, what we have to do is we have to check each thing individually. All right, so first of all, this top piece. Okay, we know that that thing would be undefined when x is -2, when x is equal to 2. But obviously that piece says x cannot equal 2, and this piece is when x is equal to 2. So what we want to do is we want to evaluate f of 2, right? So what is f of 2? Well, very simple. That's what the piecewise function tells us. It's 4. All right. Then we want to evaluate the limit as x approaches 2 of f of x. Now, f of x, well, if we're approaching 2, remember that's only the top piece. So really we're just taking and evaluating the limit as x approaches 2 of just the top piece. And so we're going to evaluate that limit, right? So I do that by evaluating the function at 2. So if I do that, I get 2 squared plus 3 times 2 minus 10 over 2 minus 2. So 2 squared is 4 plus 3 times 2, 6. So 10 minus 10 is, of course, 0 over 0, right? So now we're going to evaluate that limit by factoring, right? So x minus 2 and x plus 5. Remember, you can give yourself a head start by keeping in mind that x minus 2 is going to have to reduce because we plugged in 2 and we got 0 over 0. So we reduce and we get the limit as x approaches 2 of x plus 5, right? So 2 plus 5 is 7. And so why is f not continuous? Because f of 2, which is 4, is not equal to the limit as x approaches 2 of f of x, which is 7. So very simple, that statement tells us that why f is not continuous. All right, so that's slide 35. All right, moving on, slide 36. So now basically, very similar question. So now it says find the value of k that will make f continuous at x equals -3. So it's almost the same thing. So what are we going to say? Well, we're going to say, okay, well, f of -3, which is, well, that would be k, right? Needs to equal the limit as x approaches -3. So what is the limit as x approaches -3? Well, limit as x approaches -3. Remember, if we're approaching -3, we're not equal to -3. So we're really just evaluating the limit as x approaches -3 of the top piece. So x squared minus 5x minus 24 over x plus 3. So remember, our first step here is to evaluate. So -3 squared minus 5 times -3 minus 24. All right, divided by -3 plus 3. So -3 squared is 9 minus -15. So 9 plus 15 is 24. Minus 24 is, of course, 0 over 0. All right, and so then we want to factor and reduce. So factoring, I get x plus 3. Remember, do yourself a favor. You know x plus 3 is going to have to reduce. So you write x plus 3, and then it goes with x minus 8. So I reduce the x plus 3, and I'm left with the limit as x approaches -3 of x minus 8. And so then I re-evaluate, right? So -3 minus 8 is -11. And so now remember, what must be true in order for this to be continuous? That f of -3 must equal, that looks like not equal, doesn't it? Must equal the limit as x approaches -3 of f of x, right? So if that is true, then this thing will be continuous. Well, k equals -11, right? K is f of -3, and the limit as x approaches -3 is -11. So k equals -11. That is what must be true in order to make f continuous. All right, so that's slide 36. All right, and then slide 37 is similar as well. All right, kind of the same idea. All right, so now it says find the value of c that will make f continuous. All right, well, what does it mean to be continuous at x equals -1? That means that f of -1 is going to have to equal the limit as x approaches -1. All right, so what is f of -1? Well, that would mean I plug -1 in for x in the bottom piece, right? So that means c times -1 minus 3, or negative c minus 3, right? Okay, now that's f of -1. Now we need to evaluate the limit as x approaches -1, right? But now when we look at it, remember we have x less than 1, x greater than or equal to -1. And so now we're going to evaluate the limit from the left of f of x, and then the limit as x approaches -1 from the right of f of x. Okay. All right. So limit as x approaches -1 from the left. Well, the top piece is immediately to the left of -1. So I'm going to plug in -1 for x, remember. So c times -1 squared plus 5. All right. And so -1 squared is 1. So this is just c plus 5, right? And then the limit as x approaches -1 from the right is going to be plugging -1 into the bottom piece. So c times -1 minus 3, or negative c minus 3. So now, what must be true? Well, the limit from the left must equal the limit from the right. So in other words, c plus 5 must equal negative c minus 3. And so if those two are equal, then they will also equal -1, of course, because f of -1 is negative c minus 3. And so if I solve this, then I will find the value of c that makes f of -1 equal to the limit as x approaches -1 of f of x. All right, so I'm going to solve this. So add c to both sides, so 2c, subtract 5, so -8, so c equals -4. So if c is equal to -4, then that will make f of -1 equal the limit as x approaches -1 of f of x, which means that f will be continuous at x equals -1. All right.